How's it going? Pretty good? Yeah? Any questions? How'd you like the reading? Yeah? No? There's one announcement I wanted to make. We've done a few requests we've had for extensions on the projects, and we sent an email to the whole class saying we only give extensions with a dean's note. That's not us trying to be mean. That's us trying, like, the Dean of Student Life is there to help you guys, and I've had only positive interactions with them. So if you're having trouble of any kind, I encourage you to go to them, because they'll try to support you sort of holistically. They'll try to figure out what's going on, and across your entire curriculum and whatever, like all the courses that you're taking, and they'll try to find ways to give you some slack and cut you a break to kind of get through the semester. So we don't want to be in the role of doing that, like on just for this class. I'd rather, if you're struggling or you're having trouble, go talk to them, and they will sort of holistically support you. So I hope that I wanted to kind of try to make it sound more. It's not. I don't want it to be like this barrier to help. It's trying to provide the right type of help from people who really know what they're doing and whose job is to give it to you. All right. So we're finishing up we finished our unit, our first big module for the course, so that's kind of cool. So we just finished talking about searching and scoring and kind of our big algorithm for AI. And today we're gonna switch gears a bit. We're gonna get a lot more theoretical for the next couple of lectures. But we're gonna try to keep it connected to, still connected to like the searching and scoring stuff that we were doing with breadth-first search and stuff before. So the topic of the second module is uncertainty. It's what do you do when you don't know, when you're not sure? And this whole state of being unsure, I think it's kind of hard for people to be in that state. Like a lot of people don't like not knowing, not having information. And we as people kind of have this tendency, when we don't know something, like a lot of times what we do is we tell ourselves a story about it. When I took this leadership training, and they said, like, when people don't know, they make stuff up. Right? You fill in the blanks. You try to fill in the gaps of the story when you're not sure what's going on. And that can be really powerful. It can help you have insights and figure things out and have amazing new breakthroughs by that process of trying to fill in the gaps. But it can also get you into trouble because you can think you know when you really don't know. And sometimes holding back and sort of saying, I'm in a state where I don't know, and that's the best I can say about this state. Like I don't know. There's uncertainty, and I can maybe quantify the uncertainty, but I can't really make a firm determination. And sort of being aware of that dichotomy, I think, is very important and powerful for a lot of different applications. So we'll be talking about that today and in the next class, and maybe the whole rest of the semester too. But we're going to start by being very foundational about it. So before we do that, I wanted to go through a few more discussion posts. So you guys are doing a really great job of coming up with awesome state action spaces and awesome applications of AI. And I think reading these posts and looking at the problems that you come up with is one of my favorite parts of teaching the course, sort of seeing the things that happen. So this was one about an NBA offense, so that's like basketball. My son loves to play basketball, by the way. He like goes underneath the basket, and like he's like this tall though, and he like tries to throw the ball into the basket, and it's like 5 feet too short when he throws, but he still tries because he thinks it's really cool. So this was an AI that plays basketball. So one possible application is to find something that can figure out the optimal shot in a basketball game. And this kind of problem is very interesting to roboticists, so trying to make control algorithms that do this. So the state space is like, where are all your teammates, and then where's all the defenders? And then the actions are pass, shoot, or dribble to try to move the ball around the court to a better spot. The transition model is what happens when you do that. And this is probably non-deterministic, not only because there's error in the way that when you throw the ball, it might slip or something, and it might not go where you think, but also because you don't get to control what the other guys are doing, right? So this is back to like alpha-beta pruning, kind of, where they're all picking their own actions, trying to optimize the other guy's reward function. But it's all happening in continuous time. There's not this nice turn-taking that we had in chess, where you move, then the other guy moves, and then you move, and the other guy moves. It's all happening in parallel at the same time. And then the cost function is sort of the shot clock and the risk of this. So we're starting to, when we define this, we're starting to see, thinking about not only quantifying the uncertainty, but also, and as we'll see in the third and fourth units, the costs of things, right? So not only might you not know, but as you make different decisions, those decisions might have different costs. And then the goal is scoring a basket. And then people can do lots of statistics and stuff to figure out the probabilities of different things happening. There's an interesting blog about like NFL that looks at NFL football statistics and tries to analyze different moves that the coaches are making based on what's worked in the past. And I think these are really interesting prediction problems. So I wanted the other sort of real-world application of this kind of idea is in robotics. So who's ever heard of RoboCup? Some of you. So there's this robotic soccer competition where the idea is to make robots that play soccer. So this is a video from the trailer of it. It was in Brazil, so that's in Portuguese. And they have like a ground wheeled robot league. So these are like wheeled robots driving around. And then they have, so this is more wheeled robots. And they're autonomous, right? There's no person doing it. Taking the shot, doing passes. And then they have a leg league. So these are nows. That happens. So it's a really big deal. A lot of people are doing this. And it's like the state of the art in robot control and planning and stuff. In some ways, it's as hard as it gets. There's a simulated league, too, so people who don't want to build their own real robots. And then they have full-size humanoids. That's an Asimo robot. And then this is a new division of it, RoboCup at home. So like robots that operate in the house doing things like cooking and stuff. So I'll stop it there. This is like the trailer for last year's event. But that's a pretty large competition. Lots of people participate in it. And I think it's really cool, like watching these teams and how quickly they're moving and how fast they have to respond. It's like extreme AI or something to make these robots do stuff. So another example from the forum that I really liked, maybe I talked a little bit about this, is because it also connects to my research, is the idea of an AI that takes a set of ingredients and then outputs a recipe to produce a good tasting meal in as few steps as possible. And I think this has a lot of potential for lots of different applications. So like the state space is combinatorial, so you're combining all the different ingredients in all the different ways. The transition model is actually really complicated. So in our research, somebody who took the class last year, Kevin O'Farrell, spent the summer trying to encode a transition model for cooking. What happens when you mix flour and water? Like we make this, you get a dough, right? And we try to encode these transition dynamics so that our robot can predict what's going to happen and sort of predict what happens in these ingredients. And then there's some kind of cost function. So maybe one for adding new ingredients, and then cooking is hard, so maybe you want to make it as quickly as possible. And then the goal state is very fuzzy. What tastes good? And that's very subjective to you and your preferences. And I really like this comment from, I see it's Lee. Actually, where is Lee? He's not here today. So Lee's been working in my group as well on a cooking game. And he points out that this is dependent on what tools you have. So like if you don't have a baking dish, you can't bake. And if you don't have a blender, you can't puree. So there's this kind of structure to the state space. So this is a picture from our cooking research. So that's Baxter handing off a tool to somebody who wants to cut an apple. And the robot is observing what the person's doing, using this cooking state space to infer which tool to hand off at the right time. And then who remembers Watson from the first lecture, Jeopardy? Some of you? So there's this IBM AI that plays Watson. One of their applications is like cancer research and like trying to read journal articles and come up with information that helps doctors cure cancer. Another one is kind of whimsical, is this cognitive food truck that's powered by Watson. So you can actually go, and Watson will do basically this. It'll come up with novel, unusual ingredient combinations, synthesize a recipe, and then inside that food truck is an expert human chef who will create that recipe and serve it to you. So the AI is actually searching in this cooking space and trying to come up with good recipes. I think the human chef adds a lot of value. I think the AI, like it comes up with a recipe, and like the human chef probably does a lot of saving you from like the worst recipes, like just kind of knowing sort of what's like filling in the gaps in reasonable ways. But I still think it's an interesting application. And then I don't want to go too long on these, but like I like this one too. So I have a friend who's doing this, and he says he's got a profitable trader. So this is, stock market is lucrative and risky and dumber. So the idea is to have an AI that's doing day trading for you. So instead of paying 1% of your return to put your money in a mutual fund, which is managed by an expert trader, human trader, you might have an AI agent whose job is to kind of look at the stock market and make decisions. So the actions are buying and selling your stocks. You have a deterministic model in that you buy, after you buy it, you'll have it. But then also a non-deterministic model, because if you wait for some time, the market might go up and the market might go down, and you're trying to maximize your return. So my friend's AI is basically reading press releases and looking at news feeds on the internet and then making trading decisions automatically. And he says it's been turning a profit. So he's like working on scaling this up now. There's obviously lots of research in New York City, lots of firms on Wall Street doing these kinds of applications. It's very lucrative. You can sort of question its overall benefit to society, to sort of making rich people richer, kind of. But it's very lucrative, so it's worth putting up there, maybe. OK, so I encourage you guys to go look at the forum. There's some great discussions on some of these posts. Some people are sort of replying back and stuff. And I think it's really good to see the spectrum of the interests in the class. So now we're going to switch gears to probability. So this book is called Probability Theory, the Logic of Science. And you're assigned to read the first 2 chapters. And again, I encourage you to read them. Like it's very good. Like he's really a good writer. And the way that he lays out the math, formally theorem by theorem, I think the best way to get it is to just read it and think about it. So we're going to go through some of this in class today, but nothing can. I'm not James, and nothing can really replace the reading that he's doing, or his writing, basically. So before we start, are there any questions about what you read? Any comments about it? Just soaked in, there was anything confusing? Yeah, I know. It kind of starts out with this like burglar story. So he's like saying that at the very beginning, there's a policeman, and he observes a guy in a mask, and he throws a stone and breaks a window, and then crawls in the window. And what do you think the policeman's going to do if he sees that guy? Arrest him, right? So he's going to make an inference that this guy is a burglar. Do we know that this guy is a burglar? Do we know that he's committing a crime? No, we don't know. Why do we think we should arrest him? Why do you think the policeman should arrest him? What reasons do you have? Yeah. Past experience. So what are some examples of past experience? Yeah, right. I mean, right. So if you've seen robberies before, you know, it's unlikely that the owner of the store would throw a rock and break his window. It's not impossible; it could happen, but it's unlikely to happen. So there's just some, and you. I don't. Have you ever? Has anybody here ever witnessed a robbery? I haven't. Nobody has. Nobody's telling us that they have. But still, you kind of seen robberies happen. Where have you seen robbery? How do you kind of know what happens in a robbery? Yeah. Yeah, you've seen it in TV and movies. Maybe you've read in books, Sherlock Holmes or something. You read these stories about what a typical robbery looks like. And based on these past experiences, and also you've got these past experiences of what non-robberies look like, right? So like when most of us have not witnessed a robbery. So this behavior of like this guy throwing a rock at a window, it's very unusual. It doesn't match with our past experience that we've witnessed firsthand. On the other hand, it matches with our experience of like these bad characters doing nefarious behavior. And so based on these past experiences, we can sort of think, okay, this is probably not a good thing. But we're not sure. Can we ever be sure? Do we want to be sure? Would it be good if we could be sure? Yeah, I see people nodding. I think it would be good. I mean, we would never arrest the wrong guy. We would never let a criminal go free, right? Like we would be able to make better decisions if there was no uncertainty. But can we ever actually get there? Can we ever reach certainty? I see people shaking their heads. It's kind of a philosophical, moral question, maybe. But I think it's very difficult to reach full certainty about anything, really. Like, we're always observing the world with limited perceptual input. We can only see a certain part of the world with our eyes at any one time. And we don't know what's happening outside. Like, probably, it's raining a little bit, but maybe the rain stopped. We don't know. And so we're always operating in these kinds of uncertain environments. It's the norm, and not the. It's normal to be uncertain as opposed to abnormal. At the same time, it's often useful in AI to kind of forget about that and to just model the world as if it was sure. So we're going to talk sort of going back to this overall AI algorithm where we go through all these actions and then we score the actions. You can sort of think of this uncertainty stuff as sliding in inside that scoring function. We're going to use these models to provide a principled mathematical framework for telling us what the right actions to take are under uncertainty. So we're going to try to take uncertainty and come up with formal mathematical rules for quantifying it and manipulating it and maintaining it over sequences of operations, and then use that to drive our agent. And we'll see how this plays out throughout the rest of the semester. So to start, I want to give another motivating example. So who knows what this is a picture of? Who recognizes this? In the back. Yeah, this is JFK and his wife, and the governor, and the governor's wife, Governor Connolly, I think his name is. And he was shot. He was assassinated, I think, in 1963. Yeah, 1963 on November 2nd. So the anniversary is coming up. In Dealey Plaza in Dallas, Texas, he was coming up for re-election, and he was going on like campaign visits to different places. And his route was like published in the newspaper for weeks before, which is kind of silly because it gave somebody who we don't exactly know what happened time to like make a plan for what to do to assassinate him. About 70 minutes after the shooting, Dallas police arrested Lee Harvey Oswald for the assassination, for shooting Officer J.D. Tippit. So the question sort of is whether Oswald shot Kennedy and whether he acted alone. He was arrested with a gun, and there was another officer of the Dallas police who was murdered that day, shortly after the assassination. And then a few days later, so this is 2 days after the assassination, if you could imagine this, Jack Ruby, Oswald was being moved from one prison to another prison. And during that move, he was taken out in a public place, like being transferred. And Jack Ruby came and fatally shot Oswald. So then Oswald was dead. And so there couldn't be like a trial, and he couldn't go to jail. So there was this question ever since, what happened during this time? What happened to cause the death of JFK? So what do you guys think happened? There's been movies about this. There's books about this. If you've ever been to Dallas, you can go visit Dealey Plaza. And there's a museum that kind of gives all the different evidence. And then there's like crackpots with exhibits. So like, there's the grassy knoll, and you can go on the grassy knoll, and people have like posters explaining what they think happened, what their sequences of events is. So who thinks that Oswald acted alone when he shot? A lone gunman? Some of you? Yeah, I do. I think I'm not sure, but I think that's most likely what happened myself. Who thinks that there was a conspiracy? Some of you? Not sure? A few of you? And who's not sure? Who really has no idea? Not enough information. Most of you. Good. I like that. So that's good. Acknowledging that your own uncertainty is sort of the first step towards fixing it and collecting more information. All right. So we're going to talk next in terms of investigating this question and how can we're going to collect information and try to come to a determination about what happened. And the first way of thinking that we're going to explore is deductive reasoning. So this is this mode where we're going to pretend that there is no uncertainty. We're going to pretend that we know we know the truth values of propositions for sure, and we can sort of reason about them step by step. So here's an example of a deductive reasoning rule. This is called modus ponens. If A is true, then B is true. Do you guys believe this? Well, it's just a statement, right? It doesn't, you don't necessarily believe anything, right? So then we can say A is true. So what can we conclude from that? B is true, right. Therefore, B is true. So do you believe that? That's a little proof. Why? Why is that true? It says so, right? It's very hard in some sense, like the argument when these rules were proposed by the ancient Greeks, like these rules, like anybody who didn't follow these rules, you could fool them. They would not be acting rationally. They would make decisions that were not in their best interest. They would come to false conclusions about what was true in the world. Here's another one. If A is true, then B is true. B is false. So what can I conclude from this? What? A is false. Right. Yeah? No? No? Why? Say more things. No, it's true. Yeah, OK. Right, so this is like contrapositive. So the way to sort of think through these is to like work out the truth tables, which we'll do in a second. So the high-level idea is that you can come up with these rules, and like this is sort of math in a nutshell. Is you come up with a small set of these axioms, and then you come up with some of these theorems, and you apply these rules of deduction, and you come up with new statements, new theorems. And the way that you prove something is by finding this chain of deduction, deduction after deduction after deduction, to get to a new thing that you didn't really know before, sort of by applying these. Yes?
Did you say the second set of statements is accurate?
If A is true, then B is true. B is false, therefore A is false. I think it is true.
Really?
Yeah.
I don't.
OK. Good. So let's try to draw it out. What's that? We don't know what A and B are. Yeah, maybe we should, I don't know. So we kind of talk about, if I go forward, we'll talk about what A, maybe I'll skip forward and talk about what A and B are before we talk about plausible reasoning. So I guess I don't have slides for that. So let's say what A and B are. I thought I did, but I don't. So what are A and B? Yeah. 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 Right. A and B are statements about the world that have some truth value. And he, in the book, he kind of goes, he makes the point that they're supposed to have some kind of objective truth value. So like, so the statements that Lee gave, it's raining and it's wet outside. We could all go out and check, or we can look outside the window and see. And we can kind of, most of us would probably agree, if there's water coming down from the sky, that it would be raining, and otherwise it's not. What's an example of a subjective statement? Yeah.
It is raining, therefore I'm sad.
Yeah, I hate this weather, man. Maybe this weather makes me sad. I get to decide how I feel, but this weather sucks, right? A value judgment. Maybe most of us think that, but like some people, my husband actually has really bad allergies. He thinks this is his favorite weather, like this drizzly rain. It makes him so happy because it's not raining enough to get wet, and yet it's raining enough to get the allergens out of the air, and it's like his favorite weather in the whole world. So these kinds of subjective judgments about what the weather is, like maybe AI is awesome or AI sucks, like either one. It's your opinion about the topic, and so what these propositions are supposed to be about is things that are objectively true. Now, really, they could still reason about opinions. It's kind of garbage in, garbage out. So the claim is that for any proposition, A and B, if you accept the claim that if A is true, then B is true, and you accept the claim that A is true, then you'll be forced to conclude that B is true. You can't be rational otherwise. All right? So for the one down there, I think the right way to do this is to make a truth table. You guys have done truth tables way back in like high school algebra. All right, so we'll go 0, 0, 1, 1, 0, 1, 0, 1. All right, so we are in the, and then let's fill out A implies B. So I'm just, here I just enumerated all the values A and B could have. They could be true or they could be false. And that's all I care about them for the purposes of this deductive reasoning. All right, so A implies B. Is that true or false if A and B are both 0? True, yes. We haven't really defined A implies B, so I'm relying on your past. And we'll actually, later in class, we will define it. So, OK, A implies B. A is false. B is true. True, true. Oh, I see. You want me to go down here. What's this one? False. This one. Good. All right. So now B is false. So let's circle the ones where B is false. All right. What? What's that? You think the first one is actually wrong? A is true, then B is true.
No.
A is true, therefore B is true. So if A is true,
It's the third one, I'm sorry.
it's the third one. What? If my circle is wrong?
No, that's fine.
OK. B is necessary for A to be true.
Because if we accept that if A is true, then B is true, if B is false, A cannot possibly be true, because if A were true, then B would be true.
You haven't accepted that, that's a 0 there.
Well, if you don't accept it, then you don't have to.
Yeah, basically this table, which is reason about A, there will be, we don't know where A is.
And then you don't have to.
But let's the things change. It's not true.
OK, I confused myself. Is anybody unconfused? So I would have thought, is this, you know what? I think we should go forward in class and code them up, and then come back to this question. I thought this was a contrapositive inference, right? So like if B is false, so like B is false implies A is false, and then it's the same thing over again, right? So there's a little proof you can derive from that. And I thought we would be able to see it from the truth table, but I'm blanking on that. Does somebody see it? Yeah?
No,
Well, if A is false,
Yeah.
you can't say A is true.
Yeah.
So 0 can go to either 0 or 1. So the first one is fine. The third, the A being true and B being false is the only value that can't happen.
A being true.
the second one you circled
Y-
is the only thing that cannot happen.
The first one shouldn't be circled as 0, 0.
OK.
I think you're just circling the cases where B is false.
Yes, that's what I was trying to do. Because I thought that was, so if A is true, then B is true. B is false. I thought we would get that. Oh,
If B is false,
yeah.
the only one that's not circled is A is false.
B is false.
A has to be false because the A is true circle. That can't happen.
This can't happen? I'm just not.
What is the question?
The question is, so the second inference, somebody didn't believe it. I think it's true because it's a contrapositive rule, right? It's got to be true. And I was trying to derive it from a truth table, and I thought that we would be able to prove it that way, but I'm failing. And some people are trying to explain it to me, but maybe, yeah.
So in our second one,
Yeah.
B is false. That's 0. We circled the two situations with B being 0.
Right
And
here.
then we checked to see if our first statement is true. And we're assuming our first statement is true, so it's the first statement.
Oh, right. OK, good. That's very good. OK, does that make sense? Everybody, thank you very much for saving me for my hull. So right, we circled the two cases where B is false, but we also have this statement that if A is true, then B is true. And here, it's not true. Right? So we can cross this one out, too. So the only one that matters is, the only one that's active is this one. And that gives us A is false. OK? Do you believe me? OK. Or are you just ready for this topic to be done? Are you just ready for this topic to be over? OK. Excellent. OK. So we'll come back to these truth tables when we do probability. We'll be filling in joint probability rules. And it's very similar. Like, if you get confused, you can always go back down to truth tables. And eventually you can sort of puzzle out exactly what's going on. So we'll keep going. All right. So then, so these are rules that are kind of always true. Right? Like we can work out, we can actually prove them no matter what A and B are. We can apply these rules, and if we know things for sure, we can come up with more true inferences. And that's how math works. You come up with inferences, you apply deductive rules like that, you come up with more true things. So Jaynes in his chapter is contrast this with what he calls plausible reasoning. So here's a rule of plausible inference that he gives in the book. If A is true, then B is true. B is true. Therefore, A becomes more plausible. OK? So this is it true that if B is true, then A is true, that we know A is true? No, right? Some of you are shaking your heads. And maybe at risk of getting confused again, let's go back to the table. So if A is true, then B is true. B is true. So let's circle the ones where B is true. There we go. All right, and in this case, there's two ones here, right? So we can't cross either one of them out. And we have a 0 and a 1, right? A could be 0, A could be 1, and we cannot make a determination deductively about what's happening. But usually when you cover this, like when you do your geometry proofs in high school or whatever, they cover this a lot. Like they say, like even though B is true, maybe you want to think that A is true. You're not allowed to do that deductively. But Jaynes is pointing out that there's a very strong intuition that we have. If A is true, then B is true, therefore A becomes more plausible. We think that's true. So like if we have a rule, isn't good weather today, right? So if it's raining outside, then the grass is going to be wet. And then we know the grass is going to be, we know the grass is wet. We observe that the grass is wet. It kind of seems pretty plausible that it might be raining, right? You kind of feel that intuition. It's kind of driving you, right? So this intuition, which deductive logic just says, well, ignore it, it's wrong. Jaynes is like, well, look, this is such strong intuition. Let's try to come up with some mathematical rules that support this intuition, that make this intuition work. That's sort of the point of the math that he's doing. So here's another one. If A is true, then B is true. A is false. Therefore, B becomes less plausible. So now let's go back to the truth table. I'm going to erase my circles. OK, so A is true, then B is true. A is false. OK, so here's these two. Therefore, B becomes less plausible. So again, if we look at B, B could be 0. B could, these are both 1. Our B could be 0, and our B could be 1. Deductively, we're not allowed to make any statements about this situation. It doesn't let us make any new inferences using this implication rule. But somehow, it feels like good. So let's, like with our it's raining and the grass is wet. Let's say we look out the window and we know it's not raining. Do you think the grass is more or less likely to be wet? That's all you know. Like let's say that like I took a picture of the weather last year and I said it's not raining, and then I asked you to make a bet on whether or not the grass was wet. Which would you bet? What? What's that? You'd bet that it's not wet, right? Like you kind of like even though deductively you're not allowed to do this, intuitively, common sense says very strongly, right? Very like you can feel like it's telling you, like, look, the grass, if it's not raining, the grass is more likely to be dry. So again, like these deductive rules are kind of breaking down. There's some kind of inference that we seem to be able to do that we think that seems like it's very useful, and it's very much embedded in our way of thinking, in the human way of thinking, that our mathematical deductive rules aren't capturing. And now here's one more. If A is true, then B becomes more plausible. B is true. Therefore, A becomes more plausible. These are, again, just different ways of, all the ways that you're not supposed to use modus ponens. But somehow finding the truth values of one correlates with the truth value of the other. So if we do this one, B is true here and here. They're both 1. A is 0, A is 1. Right? It doesn't work deductively. But this is the one that sort of connects back to the one in the book. So if A is true, then B becomes more plausible. B is true. So like if it's raining, it's more likely that the grass is wet. Maybe it just started, so the grass isn't wet yet. But it's going to get wet. And then I know that the grass is wet. So I don't even know if A is true, then B is true. Right? This is weakening, that first one. And yet still, I'm able to make these chains of implication. OK. So the sort of what we're going to talk about next is like this path from deductive reasoning to plausible reasoning and probability. And we're going to get, like, where we'll end up is probability, with the rules of probability. But to start, like, to sort of take this path, we're going to, I wanted to kind of connect it back to, like, the search that we've been doing. So this is formalizing deduction as search, right? So there's an initial state, which is the knowledge base of everything that you know. Then the actions are applying your inference rules. So like you can code modus ponens. And there's other inference rules too, right? Like the not of something is the thing, the original thing, not kind of cancels each other out. And then there's more, like you can imagine applying a chain of inferences and making that into run rule and sort of having all kinds of higher level actions that correspond to sequences of these low-level actions. And then every time you apply one of these rules, you modify your knowledge base. You add new things that you know to your state space. And then your goal is to find a path between you and the sentence that you're trying to prove, the thing that you're trying to prove. So we're going to do this, first we're going to do this kind of in a game. So who's ever heard of Lewis Carroll? Who was he? Somebody? Alice in Wonderland. Yeah, so he was an author and a mathematician. And he's maybe most famous for writing the book Alice in Wonderland and Through the Looking Glass. But he had these puzzles. So this is an example of one, where you're basically going to apply the rules of Boolean algebra, deductive reasoning, in order to figure out what's supposed to happen. So all babies are illogical. Nobody is despised who can manage a crocodile. Illogical persons are despised. And the game of these puzzles are to sort of write down each of these words are your knowledge base. So what you want to do is try to write these down in symbols. And then find a proof, find a path through the symbols that gets you to a new sentence. And of course, there's an infinite number of new sentences that you could create. You could just, for example, say not, and then not, and then not, and then not, and go forever. You're trying to find a witty sentence that's kind of cute and clever that uses all three of these rules. OK? So why don't you guys spend a couple of minutes doing this with your partner and see if you can figure out the answer. And then we're going to go back and introduce some more notation for truth values and statements and stuff, and then see if that makes these easier to solve. So go. Do it. Another 20 seconds. All right. Who wants to share? Anybody think they know the answer? In the back? Yeah, good. Now, how do you come up with the answer?
So you have like sets of people, there's lots of people, and there's like people who can't try out. Those two are separate.
Yep.
And babies are some subset of lots of people.
Yeah. Yeah. Right. So there's this like despised chains, and despised people can't manage crocodiles. So like the first two kind of connect, and then the first one, A, connects with C. Right. Illogical people are despised. Who found this hard? I think it's hard. No? So you think it's easy? Did you all get the answer? Yeah? Oh, good. Okay. I think it's hard. All right. So the way that I like to think about this is to sort of, and the thing, and maybe this is too easy. It's kind of a puzzle designed to elicit combine these rules of deductive reasoning. And and sort of when you confront these problems in real life, it won't be this. They won't pull out just the 3 things that you need to do. That you need to use in order to make your inference, and sort of figuring out which 3 things or 4 things to focus on, and then figuring out the chain of reasoning between them is sort of the path to coming up with new insights. And I think it's worth kind of going through how to formalize this and sort of give you tools for thinking about it in a more formal way. So to do that, we're going to basically use the same notation that James was using in the book for Boolean algebra. So A and B are propositions with truth values. So not subjective, but objective. There's going to be no uncertainty about their truth values. We know them. We know what that it is. It's either true or it's false. And then who's sort of seen this before? What's A, B with no operator between them? A times B, kind of? How do you read that? What's that? Yeah, A and B. So if we write out the truth table for that, what does it look like? A, B, A, and B. 0, 0, 1, 1, 0, 1, 0, 1. 0, 0, 0, 1. Good, right? So it's whether it's true when they're both true. What about A plus B? I'm going to move up my slides so I can just make a. Yeah, or. A plus B. Right, true if either one of them is true. A implies B we already did, so we won't do it again. But we could do it if we wanted. Let's do it. 1. 1. Good. And then not A. 0, 0. Yeah, so it doesn't change. We're just reproducing it because we had this 4 things. Yes?
What are more either set logic or programming ways of doing A implies B? Because I can think I guess what can I make an analogy of it to the way that we did with the other ones, you know?
Yeah, we're actually going to do that. So what we'll do, I think it's, I was going to do it next. We can do this now. We'll actually write a program of A implies B. So we'll write a function that takes in A and B and returns the truth value of A implies B. You can think of it, so from a logical perspective, it's just, this truth value thing. It's just like and or. I can take in the truth value of A and the truth value of B and output the truth value of A implies B. And we'll do that. So who knows what NAND and NOR are? Who's heard of that? Yeah? Not and not or. So bear with me, and then when we get to the code, you'll see this. So NAND of A maybe I'll write it as an expression. That might be better. So the not of A and B, and there's no comma. That's NAND, not AND, NAND. So what's that? 1, 1, 1, 0. And then what about the not of OR, A plus B? 0, 0, 0, 0, 0, 0. Good. OK. So who's heard of those operations before? Some of you? Where are they used a lot? In circuits, yeah. Why? Do you know why? What's that? Yeah, it turns out it's easy to make in for physics reasons that I don't really understand. Like when you're making a chip that runs on your computer, it's a lot easier to make a NAND gate than it is to make an AND gate. For physics reasons that you can go read about it, but I don't understand. And it turns out a lot of our circuits and our computers are built around not AND gates or not gates, but NAND gates. And why is that OK? Like if I just have NAND gates. What's that? Yeah, right. So I can take NAND and I can make a NOT. So if I have NAND, how do I make NOT? Yeah. So let's call it as a function. NAND of what? And A and A, yeah. And A. So let's do that. What's that? Yeah, right. So it in fact is not A, right? So we could do it just by finding the not A and going 1, 1, 0, 0. The other way we could do it is by kind of figuring out that if I take NAND of A, so it's the not of A and A. So if A is 0, then NAND of 0, 0, which is right here, is 1. OK? You see that? And then the NAND of, well, I can't, this one doesn't matter because A has to be the same, right? And this one doesn't matter. So the NAND of 1 and 1 is 0, 0, 0. Yeah? So I can take a NAND gate and I can just do it kind of twice and I can get NOT. And it turns out I can get everything else too. I can get NOR and OR and 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 everything else. What about not NAND, but just AND? AND. Can I define NOT in terms of AND? I see some head shaking. You can't do it. So you need, basically with AND, there's no way to construct a negator. And we can see this by going through and plugging in 0, 0, 0. It's yourself. Like the only thing you can really do is AND yourself to yourself, and you get the same thing, 0. If you AND a 1 and a 1, you get the same thing. It's not a NOT gate. There's no way to get NOT out of just ANDs. You need the NAND, and then you can get NOT, and then you can do everything else. So let's do this in code. They stole my chair, too. Here's a chair. And this goes back to your question about implies. Operators. All right, so here is some code. And I defined a NAND. So why, if NAND is so fundamental, why does Python not give us NAND instead of AND? What's that?
It's like less intuitive.
Less intuitive, yeah. Like so even though everything's running on NAND under the hood, like we don't think that way. We like to think about AND and OR and NOT, and we don't want to limit ourselves in our thinking just to this one operator. So because of the hardware constraint that like building NAND gates is easy and NOT gates is hard, we build everything at the hardware level out of NAND gates. But like when we program, we give ourselves access to everything. So like this exercise here, so I put this Python program where I define NAND. I've got it highlighted up there. In terms of AND, it's kind of it's exercise to understand that NAND we can use NAND to define everything. It's not so much an exercise in like how we would really want to be programming. We just use AND and OR because it makes sense to us. So here is not A. So let me run this program so you can see what it does. So here it's printing out A and B, and basically this loop here is just doing the thing I was doing on the whiteboard. It's looping through. What's that? What? My screen is too high. Oh, sorry. How's that? Did I drop it? There we go. All right. So you can see in that truth table, it's basically printing out the truth table. A is true, false, false. B is true, false, true, false. And then it's calling, what's it calling right now? NAND. So it's printing out this truth table, right? True and true is false, because AND would be true, so the NAND is false. True, false, true, false, true, false. And false, false. NAND, AND would all be false, so NAND is true. So it's just printing this out. So what we're going to do is implies. And actually, I changed the code a little bit so that it could print out the operation. So instead of saying operation equals NAND, I'll say operation equals implies. All right, so I run this. It says implies isn't defined. So how can I define implies? What should the arguments be? And B, yeah. So first, let's try to define it in Python. So like we can use if statements and stuff. What would you do? Yeah, that's good. So maybe we can try to do it like directly though. Like if A is true, then what? Then, right, well, so B can be true or false, right? So if B is true, then what should it be? True. Else? Return false. Else? Return true. I think so. C. All right. Does that match our truth table? It's blocked out right now. Is that good? I think it's good. Yeah. All right. So now how can we write this in terms of NANDs? I'll save this. Implies Pythonic. All right. Implies NAND B. So we're only allowed to call NAND. So I heard somebody say, yeah. I'm going to call it just NAND. Should we try it? NAND. Yeah. What's that? Yeah. So does that kind of make sense? It's kind of a twisty little thing. Like we could define, we could have used our not. So I redefined not in terms of NAND up here. We could have used that, but just so it's all pure. You know, just in terms of NAND. So does that answer your question about how this looks in code?
Oh, yeah.
Yes.
Oh, wait,
That makes sense?
what is implies Pythonic supposed to be doing?
The same thing. So the functions when run return the same value. I wanted to write it in using if statements because that's kind of like if implies is sort of an if statement, right? So I wanted to kind of show the control flow. So like if A is true, then and if B is true, then return true, else return false. Otherwise return false. So it's the sort of the way that you really would write implies if you were really writing this in Python. And that kind of warmed us up, and then we did it in NAND, which is kind of the brain teaser way, you know, just demonstrating that any function you want, you can cache it all the way down to NAND gates. And that's what your computer really is doing when it's computing things. It's going all the way down to NAND operations. Okay. So now let's go back to our brain teaser and try to apply this notation to it. So we'll do it with an example first. So what we're going to do, and I'll give you another one and ask you to do the same thing, is define propositions. And again, maybe this seems silly, and maybe the brain teasers are easier for you than they are for me. I thought they were pretty hard. This idea of like we're going to define these notations, but I find going to this sort of mathematical language, especially as we get to probability and starting to manipulate the equations, to be a very useful mental tool to use in thinking about these problems. And when we do research and we define new models, this is the style of what we're doing. We're like reading, we're thinking, we're trying to write down what we think is true, and we try to write down propositions for it, define sample spaces, and then use the rules of inference, deductive inference or probabilistic inference, to come up with new things that we can infer from the things that we already know. So if we sort of take these as our statements, as our A's and B's. So B, I'm picking letters that are kind of intuitive, maybe. So B is it is a baby. L is it is logical. And M is it can manage a crocodile. Okay? So now so if we just take these as our statements, what does A correspond to? Is in a logical expression. You don't have to do it just in ands. We can go back to ands and ors and nots. Yeah. Yeah, B, so can you say like B and L? Yeah, B implies not L. Oh, it is despised, sorry. B implies not L. I forgot the last one up there. All right, what about B? Yeah, so M implies not B. Nobody can't manage a crocodile means you're not despised. Okay, the last one, illogical persons are despised. Yeah. Yeah, not L implies D. Okay? So now that we've done that, like look at B and not L and M and not D and not L and D. Now can you kind of see, you can kind of do symbol manipulation, right? To come up with the final thing. So does anybody, so the final thing was I think I have it up here. Okay, it appears. So babies cannot manage crocodiles. So I get B implies not L. Wait, where's my laser pointer? Did it die? Anyway, no laser pointer. B implies not L implies D. And then I have to switch things around a little bit to get M implies D. So B implies not L implies D. And then D implies not M. That second one is switching. So I get B implies not M. Does everybody see that? I'm kind of waving my hands a little bit, but we can go through it slower if you didn't. We did the contrapositive rule that we had to derive so hard on the whiteboard, on the blackboard. But we did it. And we like this one just because it uses all, we could have derived lots of things from these formulas, but we like this one because it uses all three and it has this kind of witty thing. Babies cannot manage crocodiles. So now what I want you guys to do, here's another one. I liked it because it was about astronomy. He has like this, like there's web pages, they have like just pages and pages of these puzzles that Lewis Carroll came up with to help teach the rules of syllogism and deductive inference. So I want you guys to take a stab at this one and try to do it in the same way. So define variables for the statements. So 3 or 4 different statement variables, and then convert each statement A, B, and C into a logical predicate, and then run inference in that to get to the answer. Take a couple of minutes to do that at your seats. Go. You can talk to somebody sitting next to you. Okay, finish up. So what are the statements that you guys used? What's one statement? Yeah. Louder? So first of all, let's define our vocabulary of statements, right? So like, T is what? Is a terrier. Good. It is a terrier. What else? W. W is? Yeah. W. It wanders. Among the signs of zodiac. What else? C. What's that? C is it is a comment. Good. What else? H? Yeah, H has a curly tail. Okay, so now let's translate A. Is that all? Any more? No more? I think so too. So you can see these statements, like objective, subjective, it's whatever you put into them is whatever they mean. The AI system or the deductive logic system doesn't really care. It just cares once you've got them, sort of the symbol manipulation crank tells you what to do with them. So now let's try to encode our knowledge base. So A, no terriers wander among the signs of the zodiac. What's that? So terrier, T, yeah?
T implies not W.
T, let's write that down. Not W. Yeah, I think, so no terriers makes me want to say not T. Let's write not T down. And I think there's definitely W because there's some wandering. So no terrier, yeah, W implies not T. Are these the same? Yeah, it's just a contrapositive of each other. The reason I prefer this one is it's really almost aesthetic, right? He says no terriers, like I really want there to be a not T. But like in this case, it's almost better because it's reflecting the order that they put the statement. So we could go with either one. And then we could derive the other one. We could use our contrapositive rule to get that. Good. B. Nothing that does not wander among the signs of the zodiac is a comet. W implies. What's that? Tell me that. W implies not W implies not C. Okay, so not W is, it doesn't wander among the signs of the zodiac, is not a comet, right? There's a lot of negations in there, but I think that's right. All right, nothing but a terrier has a curly tail. Yeah?
Is that the same as W implies C?
W implies C. What do you think? People are saying no, right? So that's another example of deductive inference. So like it kind of, you'd like that to be true, right? Like W implies C. But in fact, it's not true. And we could draw, we're kind of running out of time, so I'm not going to draw out the truth table. You could draw out the truth table and see that's not implied. That said, it's very plausible, right? And what we'll do next class is we'll go back to these plausible inference rules that seem so awesome, but they're not licensed by deductive reasoning. And we'll show how the rules of probability give rise to them and sort of make them happen. C. Yeah. T implies H.
So T implies H, H implies T.
T implies H, and H implies T. Yeah, I think you just need one to get the answer. But I think both are common. So then what's the answer? What? C implies not H. Therefore, after lots of steps, C implies. So what does that mean in words? Comments don't have curly tails. Yeah, yeah. So this is my variables, different letters and stuff. But yeah, C implies not H. Different letters, but same math. OK, cool. All right, so now what we're going to do, so you can kind of imagine this. And if we go back, actually I'm going to go back to the state space slide. This kind of inference that we're doing, where we write it down as a knowledge base, and then we run inference, we can frame this as an AI search problem. And this is one way, where we have the knowledge base, and we're given, and we were doing this, right? Like we were defining our knowledge base, our statements, and the knowledge that we had about those statements. And then the actions are the inference rules, and when the result of those actions is adding new statements to the knowledge base. So for example, in our contrapositive example, we could have taken one, and then one of our rules could be the contrapositive rule. So like A implies B. If you see a rule like that, then you should add not B implies not A. Another rule could be like A implies B, and B, if you see or A, if you see both of those rules, then you should add B to your knowledge base. And you can just code this up as breadth first search. So I have some code to kind of go through what that looks like. So let's do that. All right. So here's our statements. A is, I defined them already. And this is the hard, like typically, when you're applying these types of techniques, this is the hard part, like coming up with what your statements are and what your knowledge base is. And then the rest of it's kind of turning a crank. To do it in small spaces. In large spaces, lots of tricks go into making the inference happen quickly. Tricks like simulated annealing and greedy algorithms and heuristics and all kinds of things like that. OK, so here is like a little world. And I actually already coded up breadth first search for this. So what happens is for every, what's going to do at every iteration, it's going to do it forever. It's going to keep adding more and more knowledge. It's going to print out the knowledge base, and then wait. And then for every predicate in the knowledge, it's going to call two different successor methods. So successors 1 is for one argument successors, one argument rules of inference. Inferences that create predicates using only one other predicate. And then the 2.1 is a two-argument version. So this one takes every predicate twice, and then creates successors using both of them. And then adds, each time it's taking the result and adding it to the knowledge base, and then repeating. So let's start, I think I have, let's start with 1. So what's a good rule for 1? Let's start with something like you know, not complicated. So if you have something that you know is true, what's that? Yeah, the not's going to be false, or the not of the not. We're only going to put true things in our knowledge base. So the not of the not is going to be true. So, so what we're going to do is add something to our knowledge base, and that's going to get added. So we could just add it again, but we'll keep everything in there, so that would be adding things twice. So I defined this function up here, not. And it's not even really doing not. Like, it's just calling some two strings to add not to it. But you can imagine some evaluation code that takes in truth values and return, just like we wrote before, and plugging it into this class. So we'll do that. We'll plan the not of the not. All right. So now what's going to happen when we run? Nothing. Why is nothing going to happen? When I run this? I hear some whispering. Yeah. Yeah, knowledge base is empty. So it's like, OK, nothing's true. I'm happy. So let's add something to our knowledge base. Let's just go with A. So A is Oswald acted alone. All right, so now when I run it again, what's going to happen? Yeah. And then again. Not. And we can just keep going and doing this forever. So that's kind of boring. We're almost out of time, so I don't want to. So the next thing we could do is these two-argument ones. And we could add modus ponens. And if I had maybe gone faster, we could have constructed it. But I'm going to swap over to my cheat sheet. And you can see the implies. So we can do these two-argument ones. What we're going to do is check if is instance P implies. So if the first predicate is an implication, and if Q is a predicate whose value equals the first argument of the implies, right? So A implies B, so P implies Q maybe, and then Q is P to P1, results that append P dot P2, right? So it's saying that like if A is true implies B is true, and A is true, add the proposition value, B is true. And then if we go down to our knowledge base has these two rules. It has that A is true, and it implies A and D. So we can go Python deduction.py and kind of see if Oswald acted alone. If Oswald acted alone, then JFK was killed by a conspiracy. And then run it, and it runs inference. It runs modus ponens and says JFK was killed by a conspiracy. Who believes that? Garbage in, garbage out, right? So like this maybe didn't tell us anything new that we didn't know already. But there's actually this basic idea that AI can do theorem proving is a very large subfield of AI. And in previous iterations of the course, there was a whole unit on it, on theorem proving, built around this idea that we're going to come up with axioms and we're going to run theorem provers. Doing breadth first search sucks because you're going to get not, and you'll come up with a lot of really awesome true theorems that don't really tell you much. And then the sort of focus of the research in this area is trying to find the good theorems, kind of like when it's playing chess, like finding the good paths, the promising paths into the search space. And people think about heuristics for this, and it's changing mathematics because as proofs get longer and more complicated, it's really nice to have an automated agent checking to make sure that you haven't made any inference errors. So we're going to build on this notation as we go into probability, and we'll see that this is a generalization of logic and logical reasoning, the rules of probability, and it arises directly out of our desire for rational thinking. So if you go back to like the JFK example, like the different groups of people, both charged with determining the truth of this important national issue, and it was people who were alive at the time. My grandmother was really admired JFK, and she remembered the assassination, and she grieved even to the day that she died. She grieved over the death over his death. Like this really had a profound effect on the American psyche, and shortly after it happened, the Warren Commission report, led by Chief Justice of the Supreme Court, and a number of other prestigious people, they wrote a book. You can read the book. It's actually pretty interesting. And determined that Oswald acted alone in killing JFK and wounding Governor Connolly, and then Jack Ruby also acted alone, looking at all of the evidence. Later in 1978, so this was much later, the House Select Committee on Assassinations concluded the opposite, that scientific acoustical evidence establishes a high probability that two gunmen fired, not one gunman, but two gunmen. This is the grassy knoll was where they thought the other gunman might have been, and came to the opposite conclusion. But we don't really know. And our rules of syllogism, our rules of deductive reasoning don't really work to allow us to come to conclusions about this. So what we're going to talk about next time is like these desiderata for doing something better. And James kind of ends the first chapter that you're supposed to read with these desiderata. So we've sort of been talking about like degrees of plausibility. So the first desiderata that he says is degrees of plausibility are represented by real numbers. So it's, there's just we're talking about degrees of plausibility, more and less plausible. We're just going to say real numbers somehow represent these degrees of plausibility. He wants them to have qualitative correspondence with common sense. So when we're kind of doing these thought experiments about like if it's raining then the grass is wet, these plausible inference rules that don't follow from the deductive inference rules, we want the mathematical framework for plausible reasoning, for probability, to correspond to those kinds of plausible rules. And consistency. So you don't want to have, if you have a proof, and you can sort of come to the conclusion in more than one different way, they should both come to the same answer. You don't want a theorem proving system that lets you prove something in its negation. It should take into account all of the information that it has. So he's talking about not arbitrarily ignoring some of the information. So it's not ideological. It's just trying to reason based on what it knows. And it represents equal states of knowledge by equal plausibility assignments. So if you're equally uncertain, then the real numbers that we're using to represent the plausibility seems equal. And it turns out that just using these three, of course number 2 is kind of a big black box, but just using these 3 qualitative considerations, you can derive probability theory as the unique set of axioms that satisfies these desiderata, reasoning rationally in a plausible way. And again, I encourage you to read the book Chapter 1 and Chapter 2 to see how this happens. And we'll talk about in next class how we can go from this to probability. Thanks.